Welcome to this 88K model railroad video, and today we are going to continue on with our Rocrail Wiki Demo Layout Build. We're going to look at the test, or actually conduct a test and migration of our build into the Rocrail Wiki Demo plan. We're going to go through the migration strategy, test the sensors and switches. Then on the creation of the cut sheet, we'll go through that, touch on it, and then we'll perform an operational test. So with that said, let's get started. Okay, the migration strategy. With the migration strategy, we want to set up a series of steps that's going to help us get through and achieve our goals of rolling our module into the Wiki Demo Layout module. Now, what you want to do is first you want to create a fallback version. Take the initial Wiki Demo layout plan and then copy it. Then copy the next one and label it version or v1.0. And each time we go through, or each time you go through a particular step, you can save that file as v.1, v.2, or it's version 1.1, 1.2, 1.3. Then when you take a next version step, you'll do 2.1, 2.2, 2.3. Now this helps you maintain the integrity of Wiki Demo. And what we want to be able to do is roll our components or the layout plan into the software aspect of Rocrail with Wiki Demo and maintain the integrity. So we don't want to change any of the names or numbers or the nomenclatures that you have for the sensors and all of that, because they are already attached to other components. And if we change the original name, then Wiki Demo won't work anymore, so you'll kind of be lost. So we want to maintain the integrity of Wiki Demo so we can add our live system to it. Now you want to test each step as well, so as you go through, make sure that everything works before you go to the next step. Don't skip anything. And then always document your changes. It's important that you document things in order to keep track. And although it's time consuming, it's going to pay off in the future. So that we've got the migration strategy set. Now let's go look at our testing. Okay, here we are at the test segment, and what we're going to do is to test the sensors and the switch. So we're finally to a point where we can see something, and I know some of you guys are like, you talk too much, we want to see something move. So we're getting to that point. We're going to verify the switches and then the sensors, but I wanted to talk about the sensor itself. If you look over to the right, there's the what I'm calling the 88K sensor track, and what I was able to do is to embed the infrared sensors into the track and to try to integrate it as close or as invisible as possible. So you can see that I cut out a little pocket inside the ties itself, and position the sensors there. So at a distance, you can't really see the sensors. So I like that, and it took a lot of effort in order to get that, but it is working, and we're going to test it, and then I'm going to actually show you. But before that, I ran into a couple of issues, and I think it's important that we kind of put the pieces together, and it's concerning the LED and the sensor, or the current limiting resistor that we have to place on it. So let's swing over to the documentation so we can look at that little schematic, and we can kind of talk about that. So let's do that. Okay, so here we are. Remember, in the earlier video, I talked about the documentation and the importance of it, and that whenever I build a layout, no matter how big or how small, as you can see, I always create a design doc, because it helps me keep track of things, and then if I have to reference or have to find something, the information's there. So let's go through, before we go to that particular issue that I was talking about, the sensor and the LED, let's look at this document real quick. Here's the cover. It shows, the basic project. This is the block diagram here, the frame, and there's more to this. This is just a short portion of it. There's more that shows the lumber, the dimensions, and all of that. Here's the feeder location here. This shows me the feeders. If it's a large layout, you'll have maybe 70 or 80 feeders, and you've got to keep track of it. Also, here's the switch, same thing. The last layout I did had 53 switches. This is the wiring basics, and what it does is it shows me where I'm going to have the wiring, or the not the pins, but the drop downs for the wiring, and it gives me an idea of how to lay the panel out. Next, we've got the electronics. This is what we were actually talking about, but I'm going to go through each one of these because it can cover some things that I may not have covered in the previous videos. Here's the power. This is a power distribution. For our DCC system, we're going to use the Pi Sprog. It goes in, feeds into the, it feeds into the DCC terminal, and then it fans out to each one of the feeders. This is the 12 volts that the power supply feeds, or the basic power supply voltage that we're going to run on the layout. And then I've got the buck converters, remember, that drops down the 5 volts that we need for the ESP32. This is the power supply. This is important because you've got an operating power supply and the testing power supply. I'm using the 12 volt 600 milliamp testing power supply with the circuit breaker in it to protect my components, because if I have a wiring issue and I power it up, this will then switch. It's only 600 milliamps, so we can minimize the damage that can occur, versus the operating power supply with the 12 volts and 3 amps. That's a lot of power. It can create a lot of issues. Here's the cut sheets. The cut sheets shows me how I have the assignments made, and you can see that there's the Rocrail Wiki Demo, and then my migration Wiki Demo, and this is where we marry the two components together. Here we've got the WIO worksheet. This shows ID 34, which is the WIO node that we're using, and this is the breakout. And what I've got is like a laminated sheet that I could use the whiteboard pen to write and mark down everything that I need. This is basically what I'm going to do, and then transfer it into whatever document. Here we've got, you can see where I've transferred. I made the nomenclature, the D1 0DS, which we saw in the other video, and the assignments of the IOs. Here, this is a sensor board. This is where the sensors come in and feed into the ESP32, and the ESP32 sends the response or the event to the Rocrail server. And the last one here, or not the last, very last, almost the last, we've got the switching module that allows us to interface with the Kato switches that switch. It's a snap switch, but it's based on polarity versus like the Pico and the Atlas. It snaps, but they snap either twin solenoids, two different solenoids, or two different, or the one solenoid in two different directions. Kato switches polarity, and that's what this module does. And finally, we've got the ESP32. This is its breakout, the IOs. This is how we've got the basic designation, the sensors, exactly where the sensors are assigned and what it's supposed to do. So with that said, let's jump back to our initial point, which is the electronics, which is this page here. This is our sensor track, and if you look here, the LED that illuminates the IR, or the IR LED that illuminates and bounces against or off of the train, that intensity is based upon R1. So if the beam is not strong enough and you're not getting a response, or the receiver is not being activated or triggered, then you have to change that resistor value. And remember, we know that the resistor value, and we always think that we needed to limit the current in order to protect the LED from burning up, right? But it actually controls the intensity or the amount of current that flows through. So in some cases, you may have to increase the current flow through the resistor that increases its intensity. So for our numbers here, we're using the 5 volts, and with the forward current voltage, or the forward voltage, the current value in the data sheet, it shows that the max is 50 milliamps. So we control, if we want maximum intensity, we run it at the max 50 milliamps. But you don't want to do that, because you don't want to power the LEDs, so you try to back it down a little bit, which means you increase your resistance. So you can see that you'll be able to see this issue here whenever if you have problems with the receive of the LED beam, then change this value, and you may have to increase it. So that's all I need to say about that. The next thing is, look at, you see where it says common emitter and common collector. Common emitter and common collector shows where you're going to tap in your signal lead. And you could see there's the lead that's below the module and the lead that's above the module. And the difference is where the voltage is going to be applied. So whenever the voltage is sitting and the device is on the same side where VCC is located, that means that it's going to be constantly on. And when the LED is illuminated, it's going to cut the power off. So if you look on the right side, you can see that VCC is here at the bottom, and the circuitry is closer to ground. So whenever the LED is activated, then it's going to apply voltage to your module, or to your signal lead. So we want that configuration, because that means that on idle the sensor is off. And when the sensor is off, we're conserving power. So you don't want all 16 of your IOs drawing power being on when it's idle. So always make sure you pay attention to how you've got it configured out. And if you do see something and it's, hey, it's on, but I want it off, then this is where you have to look and change your configuration. So with that said, I'm going to end the video here. I'm going to start part 2 with us actually going in and doing the test at the bench.